702 Thunderbird Rd.
There you go.
Drive by it and come back. The Center for Educational Research.
Oh, thank you.
All right. So welcome. I want to thank you guys all for coming out, participating in this workshop. And throughout the 3 days, we hope to be as hospitable as we can to you. So please feel free to ask any questions if you need anything. We have local host Anthony Rogers and Megan Communis that will make runs to the store if we need to, if we need something so you can continue observations. So if you need anything, I hope you enjoy everything that we have to provide. And this is the first time I've had such a big outing, so hopefully everything goes well. So I want to give you a little bit of background on the Lewis Center, the facility that is just one of the 3 campuses that they have to offer for students from K through 12. So the concept of the Lewis Center was developed in 1985 by a man named Rick Piercy, who started out as a kindergarten teacher at Mojave Mesa, which is northeast from us, this Phoenix Academy. When we're outside, you'll see another facility. I believe, is it closed down right now, or? I believe it's closed down, but that's where he started off as a kindergarten teacher when he developed this concept of having a science and technology for students. So in 1988 and 1990, Rick Piercy and what he called his star leaders designed programs for an academic excellence school for students. And in 1990, the end of it, the grand opening of this facility opened up for basically science and also technology. So for all those who don't know Eric Weise, he's a student at still University of San Diego.
All right, so I'm here to talk a little bit about double stars. Now, I've been doing double star research with Dr. Schmidt for a few years. I'm a junior in college right now, and I started working when I was a junior in high school on double stars. Dr. Schmidt offered a seminar, and we observed double stars. I don't remember what it was. It was a long time ago, but we published a paper. And then next year I came back and worked again. And it's just been a really great opportunity. And I think programs like you have here at the Lewis Center are just awesome for getting students to really get interested in science and really get them started. Yes.
What happens if the stars are of equal mass? Would one still rotate around the other, or would they rotate around each other?
I wish I brought my props, because I have something that demonstrates exactly that. But, so, imagine I have 2 balls connected by a string. If they're the same mass and I throw it up, they're going to circle around each other pretty much right around the center of the string. Now, what if I have a mass on one side that's 10 times the mass of the ball on the other side? If I throw it up, the smaller mass is going to whip around, and this one's going to move around just a little bit.
Oh, so the actual observed point is that circle at the end of the green line.
Yes.
And that green
Yes.
line connects it back to the ellipse.
And it gets it back to the ellipse at the point in time that they made the observation where it should have been.
Okay. Thank you.
I have for that presentation.
decided to play around with some trig functions. And so by doing that, we decided, well, we already have the x magnitude, we already have the y magnitude. Simply put, the angle that they would be at on the coordinate plane would be tangent theta equal to y over x of the magnitudes. So we plugged in some numbers, that's what we did, and it ended up, that's how you could find the position angle. Also, as Rick was saying, that we don't want to be too confident in these sig figs here, that we can confidently report up to 10 thousandths of degrees. So although the mathematics behind it works, it's not necessarily what reflects how precise these measurements actually are. So we would probably still just report to the hundredths with some confidence.
This is a data point we had, and when we looked at it closely, we saw that the past observations, this is over 100 years of observations. You can see here's the visual again, but you can see that there's a definite S shape to them, and what this meant was that there was so here's the primary star, if you will, and here's the other one going on a very elliptical orbit, that we only see part of it here. And but it meant that there was a third star of the system that this was going around, but you couldn't see it, but we were able to, it was about an M5 star, so it's just too faint to see, but you can see the gravitational results. I use this as an example of a paper that got all marked up. So this was one that Mark did on his own, sent to me to make corrections. You'll be seeing papers like this, but then after they all get squared away, then you get these really nice papers. This is the second edition of what we fondly call the Bible, but this is Bob Argyle's edited version, Observing and Measuring Visual Double Stars. And if you only have one book, this is certainly the book to get.
Yeah, his name's Bernardino. I guess patented the idea. A flip mirror right here, an eyepiece, and a Barlow. And we were using this to observe with 10-inch Russ's camera or telescope. And the stars. So it was we put a ×3 and a ×5 Barlow on there, and the stars were just so dim that we couldn't see anything. And so that would take the effective focal length to about 300 to 500 inches. But this telescope is really nice, just perfect for this instrument. When we're observing, the double image micrometer is great in that it can make 2 images of 2 stars. So it makes 4 stars, and then you line them up or arrange them in one of these 3 ways. When you look through a normal eyepiece, they're together, and the eyepiece, when the backlight isn't inclined at all, they're together, and it appears as if it's just one double star. So you got an ordinary and actual ordinary image. Doesn't really matter which is which. You can't tell. You can't distinguish with your eye. But so green would be, for instance, the ordinary image, and blue is the actual ordinary image. And you just play around with the dials until you get a configuration like one of these.
We gotta make it say because you have to subtract when you flip it, you have to subtract 180 degrees in order to make it the same angle every time. But if it goes less than 360, then it'll be a negative number. So if you go over 360 or less than 0, you end up with an invalid number. So there's a statement that you would write to correct that. With a Newtonian like we have, and last night we read from the inner scale, but on a Newtonian telescope, you have to use the outer scale.
No, that was 19. We're going backwards, trying to pick a group. Let's try 17.
Tell me it scrambled the sequences as well.
625.58. Still looks bigger.
626 is about, that fits. It's still got a Barlow?
Yeah.
Yeah. Okay. So that's the previous one. So those two are the
Let me
last
see
in the
16.
sequence. So do we want to redo it?
Does anybody want to read
See firsthand
through one of these?
what happens?
Good.
Yeah, do one
There's a lot
that's
of
never been touched.
stuff you don't need to know.
Let's see if we can
But
find
if you
one
go to
that hasn't been
methods,
touched,
this will help
but we
you.
can note that, so if we can't, we can always go back.
We'll call this
Wait, look up the right.
Brandon,
Anyone else first?
19 didn't have the timestamp on
So 18 is the last
it, so
one.
we want 18.
And that should be
And make sure.
6.7 times 3.
Well, because
Okay, that's it.